This is about trends, looking back at what's happened and what the issues are and how it might affect things going forward. I have, Carl Ford, organizing conference, set me up with something that basically was the title and part of the abstract for a 4-hour tutorial. And he said, here's an hour. So I changed it around and negotiated to say, basically, I'll skim through a lot of history, but the idea is to point to, what are the implications and what are some outrageous things that might be happening. I'm going to list of outrageous things, but without justifying them, we can talk about them in the Q&A. And I'm going to skip through a lot of material, which you can get by getting a copy of the slides. I'm going to apologize for skipping through technical stuff and not doing a deep dive unless somebody asks in the Q&A. If you leave me a business card, I will mail them to you. Alternately, Carl Ford has claimed that he will send an email on September 8th to all conference attendees telling them where they can download copies. And finally, if you Google the words either 3G tutorial or 4G tutorial, I come up either number 1 or number 2, and a lot of this material, the deep dive stuff, is there. This specific presentation, leave me a business card, I'll email it to you. Okay, so I am going to skim through a bit of history. The idea here is to understand the way things have played out, so as to think about what might be happening in the next few years and the next 10 years with an idea of, what's the real, say, the 2 or 3 or possibly 4-year strategic planning horizon that most actual real businesses think about. Just if you want the deep dive stuff, it's on the net, or you can give me a business card. And this is just to tantalize you. I'm not going to justify all of these in this presentation, but I'd be happy to justify them in the Q&A or one-on-one or by email later. 5 gigahertz spectrum will be more valuable than 700 megahertz spectrum, and that's becoming apparent to a few people, like the TowerStream guy who gave the keynote last night alluded to that. But there's a lot of other fundamental reasons why over the next 5 years, 5 gigahertz or anything above 3 gigahertz to 10 gigahertz will actually be more valuable than 700 megahertz 5 and 10 years from now. LTE versus YMax. By 2020, it's pretty clear that LTE and its related family of GSM-related networks will be more than 80% market share, YMax less than 15%. The real question shouldn't be about YMax versus LTE. It should be about service provider versus user-provided networks, which you could roughly say is Wi-Fi versus the sum of LTE and YMax. TV white spaces, because the way the regulations have been written and so forth, they're probably a write-off. Maybe the regs will be changed. Google certainly hopes so. But the real outcome, the really significant thing that happened with the TV white spaces is the FCC certified a block of space where they authorized so-called secondary access. That is, you can use this on a license-exempt basis if you conform to certain rules that don't interfere with the primary user. And that political concept may be the way that we actually get access to the really valuable spectrum, which is the spectrum from 3 gigahertz to 10 gigahertz. So that might be a 10-year battle. But when we look back 10 years from now, the most significant thing about the TV white spaces decision won't be the spectrum. It'll be the secondary access principle. So those are just some outrageous things. So let me dive back into kind of the meat of things. Mobiles overtake fixed. Everybody knows this. But look at those lines. The reddish purple line is fixed telephone service globally. Peaked at 1.4 billion and is beginning to shrink now. Compare that to cellular, mobile phones. The real principle here is that the pink line is run by monopolies or government, typically by government-sponsored companies or government-regulated companies. The yellow line is not open competition, but it is typically an oligopoly, 2, 3, 4, sometimes even 6 or 8 competing cellular carriers. And that's the difference you're looking at there. If I had a line for Wi-Fi, not subscribers, but some other metric, the Wi-Fi line where there's true competition would be significantly steeper. And so the issue here is not about technology, it's about business commercial arrangements and regulatory legal stuff. Mobile over the years, again, I won't dive into the details of this, but basically all these 1G, 2G, 2.5G, 3G, etc. are about mobile voice. But the interesting thing is lurking in the background, and we're kind of reaching a tipping point finally right now, is what's the data capacity. The promise of IP over mobile phones has been there for 10 years, but the reality is it's only really become significant in the last 24 months. So this chart, just to give you a sense of what's going on there, we're now in the range where getting a megabit to your phone is practical in a number of places. But we've had this enormous technology change over the last 20, 30, 40 years. But in every case, commercial interests have trumped the technology in the way things have actually played out. And even more important, the legal regulatory issues trump everything. And that's the reason it's worth looking at what's going on to pull out lessons about what's going to happen in the next 1 year, 3 years, 5 years, or decade. So to zip through kind of the history of all wireless, it starts with James Clerk Maxwell, 1864, Maxwell's equations. If you're an engineer or a physicist, you can groove on Maxwell's equations. In fact, they are still completely applicable today. A bunch of other people contributed to things. Popov, the Russians have a real claim to the first radio transmission. The Indians have a real claim, and so forth. A lot of people do, but the practical matter is Marconi is the guy who devoted his life to using radio for communications. Unlike Tesla, who wanted to use radio for transmitting power, this is the guy that made it happen. By 1910, we had radios on ships, radios being used by the military. By 1920, we had broadcast radio, and this may not be the first, but it's the first one I could find, the first mobile phone. So, reality is mobile phones didn't exist until we got cellular. It was invented at Bell Labs in the late 50s, early 60s, but wasn't commercialized until 20 years later for a bunch of reasons, including computing capacity to handle the handoffs and the physical way that Bell Labs operated and so forth. The point is that the big concept was that instead of dedicating radio channels everywhere, we will reuse radio channels in adjacent cells. The early scheme came up with a factor of 7, so we needed 7 frequency sets for 7 things, and then we could reuse them. Pretty soon they figured out you could stick a tower at the corner of something and put a 120-degree angle and do a sector, so 3 sectors, and suddenly with the directional antenna you found you could do frequency reuse in a factor of 3 instead of a factor of 7, so we got more than a ×2 improvement in capacity. Commercial deployments, think basically 1980, 79, 80 for 83 for the U.S., 79 for Japan. Basically 1980, the first generation cellular technology leaked out, and by the late 80s it was becoming quite common. If you want to think what's the lifespan, it's basically 25 years. Most of it was turned off by 2005. So 1980 to 2005, a wave of technology from birth to death is about 25 years, at least for 1G. There were three systems that represented big market share. There were all sorts of other things, specific systems for emergency service and so forth, but 3 systems that got wide deployment. When we came to second generation, and if you want to think about something, think 1990. So first generation starting around 1980, second generation starting around 1990. Second generation was digital, and with one exception, everybody used a new kind of modulation called a new kind of coding called time division multiple access. So instead of having a separate frequency for each conversation, you took a block of frequencies and had, if you had separate frequencies, you needed guard bands for each frequency, which was waste spectrum. So now you take a block of spectrum that's somewhat bigger, and you go bing, 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 and you time slice the spectrum to talk to 8 people in each slice, and you use this one block with one set of guard bands to handle 8 people instead of 8 separate frequencies with 8 separate sets of guard bands. So that's a big innovation, only feasible with digital technology. There were 7 widely deployed 2G technologies with somewhat different commercial characteristics, but 7 different systems incompatible. 6 of them were time division multiple access. One of them was more sophisticated, and that was Qualcomm with something called code division multiple access. Now, it happens when we got to 3G, everybody went to code division multiple access in different forms. Qualcomm pioneered this, demoed it in 1989, deployed it in 1994, and it's what is used by everybody in Korea and by Verizon and Sprint here in the U.S. and a few other places. Much easier to migrate to 3G because they developed what became the 3G technology and deployed it as part of the 2G wave. But they were about 3 years behind the other big guy, who is the guy that won, and that's GSM. GSM got there before the Qualcomm CDMA by 3 years. GSM also got a much, much larger footprint. Cellular service deployed much more rapidly in Europe than it did in the U.S., and a much larger population much sooner because it was a uniform system with completely published interfaces, much, much more so than any of the North American technologies at that time. There were many different competing vendors. Prices came down. It became the low-cost system to deploy, so as people deployed in Asia and other parts of the world, they went with GSM because it was more cost-effective. So critical mass network effect took hold. It was very solid by the late 90s, and it was pretty clear that this was the dominant standard going forward. Today, if you take the sum of GSM and the different versions of 3G that are part of the GSM family, put them together, and that's 88% of all the subscribers in the world. So talk about market dominance. That's a family of technologies that has completely won. Also, because it is the dominant technology in the world, there's a significant payback for enhancing it, and we've seen an enormous number of enhancements over the last basically 18 years that have significantly improved the carrying capacity of how many voice calls can you put on a certain amount of spectrum with a certain amount of cell sites, and the efficiency of the system has been improved by more than a dozen, 6 or 7 of which are listed there, significant enhancements to the basic spec. So just to comment as we look across and this is, I won't dive too deep in this, but I mentioned first generation was using separate frequencies for each call, referred to as frequency division multiple access. The way you get multiple people is to give them each a separate frequency. Each frequency requires a guard band, so most of your spectrum's taken up with guard bands, very inefficient. With 2G, with the exception of Qualcomm, everybody adopted time division multiple access, where you take a block of things, frequencies as a group, with one set of guard bands, and you time share that thing amongst multiple users. And what happened for 3G is called code division multiple access, and I have a little description of what that actually means, because that's a computationally efficient thing that was only possible when Moore's law got to the point that you could do pretty fancy footwork. That's what 3G is. And when we look at 4G and future systems beyond that, there's a lot of different acronyms and buzzwords, but if you wanted to sum it up in one concept, the concept is we would like to simultaneously optimize things in frequency, time, and coding space, plus we want directionality, and we want to deal with multiple paths. So there's a whole set of concepts, and we're trying to optimize these simultaneously, and that's what the 4G discussion will be about. So when we got to 3G, everybody went to code division multiple access. This is also called spread spectrum. It's a technology that was originally developed by the military because it's a very good way of resisting jamming and other kinds of you code things so they're hidden from anybody who doesn't know the code. It just sounds like noise. And when we put a bunch of different people together with different codes, put their signals together in a common shared piece of spectrum, it just sounds like noise. But if you know the code for the conversation between you and me, we can pull it out because we got the right code instantaneously in our handsets at this time to pull that particular modulation out of the noise. Here is one way to think about it as a graphic demonstration. So what's that stuff up in black is just some mushy noise. But if I've got the pink code, it says dog. If I've got the blue code, it says cat. If I don't have either code, it's just noise. So think of 100 or 200 different signals in the same area. The black stuff would be a lot more mushy. But if you've got 100 or 200 codes, you can pull the interesting stuff out. So what was the 3G vision? This was articulated in the 90s. The goal originally was to roll out 3G by the year 2000. That would have been appropriate if you think 1G was 1980, 2G was 1990. Actually, it was 91. 3G was going to be 2000. Well, it actually ended up being 2003 in Japan and 2005 in Europe. 2007 here or something, whatever. The point is it didn't get there by 2000. The vision included we were going to have a single standard instead of 7. That didn't happen. We ended up with 3 standards. Increased data rates, that certainly happened. Multimedia support. Everybody in the telco world wanted voice, data, and video. By video, I mean a video telephone conversation. That's the holy grail of the telephone industry, even though most subscribers don't seem to want it or care. And that's in there in the 3GSM spec. It's not deployed in the US, but it is deployed in just about every other 3GSM deployment in the world. It's hardly used. More capacity, more spectral efficiency, that's obvious, and a data-centric architecture. When the specs were originally being developed in the late 1990s, the focus was on ATM because it's a telephone industry and that's where they were coming from. Eventually they realized that IP had won, and the specs got sorted out and changed over to IP, but there's still a lot of ATM stuff deployed in wireless backhaul. Amazing. Deployment took much longer than expected, partly because there was no killer data app. The spectrum that was sold, a lot of it was sold in the bubble in 1999 and 2000. The telecom bubble burst, and most of the 3G vision was driven by vendors, not by operators. Has the industry learned something from that? I think so, but only partly. Today, 3G is being deployed. It's not ubiquitous yet. 2G is where we are in reality in terms of most of the people in the world. There are 3 3G standards that are widely deployed. The first one was the Qualcomm 2G that evolved into CDMA 2000, called multi-carrier CDMA. The second is the 3GSM standard called Universal Mobile Telephone Service, UMTS, with 2 different kinds of coding, wideband CDMA and HS, high-speed packet access. The governing body for the GSM standards is called the GSM Association, the commercialization, the equivalent of the Wi-Fi Forum. They do not understand branding. They change the name of what they're promoting about every 12 months. So there are 7 or 8 or 10 acronyms: 3GSM, UMTS, wideband CDMA, HSDPA, HSUPA, HSPA, HSPA Plus. Really crazy. It's all the same thing. I call it 3GSM because that's one of the things that they've used for a number of years. And finally, there's a Chinese system called TD-SCDMA, Time Division Synchronous Code Division Multiple Access. The reason all these things happened is patent disputes. The reason that the Chinese thing may actually survive, independent of the large population in China, which makes a real market, is it's also uses a single spectral band. The 3GSM has several things defined, but the version that's most widely deployed uses 2 separate 5 megahertz channels, one for down to the handset and one for up from the handset. That's fine if you've got voice traffic, which is symmetric, but if you have web browsing, which is predominantly one way or another, you might want to dynamically change from 1010 to 18.2 and then flip it to 13.7 and back and forth. The Chinese version does that by default. It gives you a way to dynamically, on a millisecond by millisecond basis, allocate which way it's going. So the TDS CDMA is new. It's behind the other things. The only reason it may survive is it's a large market in China, and it is actually technically more efficient for data purposes. CDMA 2000, widely deployed, but less than 15% of the market. And beyond that, it's a dead end. Even though it was technically better, it got there sooner, it was cheaper for the people who were on 2G CDMA to migrate to 3G than anybody else. It was definitely ahead for a number of years there, but it couldn't compete with GSM's critical mass, network effects. The last straw happened when Verizon Wireless announced that when they were going to move to 4G, they would go to LTE rather than going to the CDMA 2000 evolution. They made that announcement in November of 2007. Qualcomm hung in there for another 12 months, and finally they announced they were abandoning their 4G thing and not pursuing it any further. So the 3GSM standards come out of a thing called the 3G Partnership Project. It's an amalgam of standards bodies from different parts of the world. These are the guys that have controlled the 3G standards and control the LTE and that part of the 4G world. They are the market leader at this point. A bunch of different acronyms for the modulation: wideband CDMA, HSDPA, HSPA, HSPA+, HSPA evolved. This is legally mandated in Europe. It's also legally mandated in a number of other countries. There are, in order to deploy it, you have to have substantial new spectrum because it's completely different modulation than the original GSM. So to keep your GSM system operating, when you put your 3GSM out, you have to have another 10 megahertz of spectrum at a minimum. The result is it was a slow start. It was behind CDMA 2000 for a number of years, but with GSM and a market share beyond 80%, there was no way that it wasn't going to win. So if you want to talk about LTE versus YMax, same thing applies. There's no way that LTE isn't going to win. Sorry, I like YMax. It's going to persist indefinitely, but it's not going to beat the 80% or at this point 88% market share. So yeah, that's anything else is just people who don't know what's reality in the world and haven't looked at history. The Chinese version, just like the CDMA battle between the European 3GSM version of CDMA and the Qualcomm one was a patent rights battle between Ericsson and Qualcomm. The Chinese are sitting there with coming as a very advanced high-tech country that's barreling ahead, and yet they have to play catch-up with Europe and the U.S. Europe and the U.S. have patents on all sorts of things accumulated over 40 years. So the Chinese basically say, well, gee, we have a big market. We have 600 million wireless subscribers now. We have 1.3 billion population. If we develop our own thing with our own patents, Ericsson and Qualcomm are not going to want to abandon the Chinese market, so they'll have to come and negotiate with us, and we'll have good terms. That's why TDS-CDMA exists. It's the same patent battle, which is the reason why we have CDMA 2000 and wideband CDMA. That was a patent battle between Qualcomm and Ericsson. This is a patent battle between China and Qualcomm and Ericsson. It is an interesting technology. It's definitely late, but it's very flexible, very well designed. It does have a few impediments. The power amplifiers are a bit difficult to build. The handsets took a lot longer than the Chinese government thought to actually get to work. But they are working now, and it is being deployed along with 3GSM and CDMA 2000. China is the largest mobile market in the world. 3G licenses were finally granted this year, and deployments are happening. 2G, 3G. Docomo was the company that was ahead of everybody else in terms of 3G adoption. They rolled it out in 2003. And the question is, when is 2G going to be turned off? Well, Docomo has implied, not committed, that they might actually turn off their 2G 2G network at the end of 2010 or the beginning of 2011. And that means that for one country and one company, 2G would have lasted basically 18 years. Realistically, by the time you get to the last guy turning it off, it's going to be more than 25 years. So we are going to see 3G technology, which is not yet dominant, peaking some years in the future, but only displacing 2G finally by sometime beyond 2015, probably closer to 2018. So the world today is 2G with 3G coming on strong. The world for the next 5 years will be 3G with 2G only turned off sometime after 2015. Meanwhile, 4G is great to talk about, great to sell to people, but it doesn't really exist in the cellular world yet. This is just some stuff interesting. How far are we doing in the 3G deployment? These figures are now 12 months old, but basically we were reaching roughly 30% penetration 12 months ago. The interesting thing is the U.S. has caught up with Europe, and the U.S. growth rate is so much faster that in the past 12 months we've pulled ahead of Europe, but we still haven't gotten to 50% penetration. What do people use it for? The answer overwhelmingly is they use it to connect to the internet. They don't use it for any of the 3G services that the operators originally envisioned. They use it to connect to the internet. Most of the first 3G deployments have been USB modems that plug into laptop PCs. The second thing is high-end feature smartphones, of which the iPhone is the most notable one. In the U.S., there's substantial stuff there, but if you look at European things, at high-end Nokia phones in Finland and so forth, no matter where you look, the second thing way behind USB modems that generates data bytes on the 3G networks is smartphones, and 80% of the traffic there is web browsing, 10% is email, and 10% is other. So the reality is none of the operators' 3G services are actually driving 3G demand. It's all internet access, like 99% of all the bytes. It may not be 99% of all the money. The money is apportioned in other fashions, but the demand there is for internet access, not for all the fancy 3G services. Another comment, there's still not international roaming, not only because we have 3 different 3G standards, but also because building a universal phone is technically very difficult because the spectrum is all over the place. All these things travel at the speed of light, which means as the frequency gets higher, the wavelength gets smaller. The cheapest way to build an antenna is directly related to the wavelength. So as the frequency goes up, the antennas get smaller. But to cover these ranges, the low-cost antennas, you need different antennas. So you end up with something like this, has multiple antennas in it, multiple radios in it, and the actual modulation, that's easy now. That's covered in digital signal processing. But the multiple radios are still built out of RF technology, if you will, and the antennas are built out of things into the back of this, and it's a very hard design problem. So it is difficult, and it will be for some years to come. Before we digitize everything. This is a quick summary of just where does everything go, and we may in fact get towards kind of closer to 1 or 2 systems. The CDMA 2000 evolution is gone. It's a dead end that's been dropped, and that leaves us with 2 things in the 4G generation which a service provider might use to provide mobile device service. So what is 4G? Actually, the interesting thing here is 4G uses orthogonal frequency division multiplexing. It's a new kind of modulation that sort of simultaneously optimizes for a number of different things. It also uses multiple input, multiple output antenna technology. The most interesting thing there is that the pioneer and the most widely deployed 4G technology is nothing to do with LTE or YMax. It's Wi-Fi. The first stuff was in 802.11a. The second stuff was in 802.11g. There are hundreds of millions of 4G things deployed. They're operating in this room right now, and they're all in it's all the Wi-Fi you use today is 4G technology. Now it's short range, 300 feet, what have you, but the next version of Wi-Fi, 802.11n, is doing a bunch of things that are driving the chip vendors in a direction that will substantially increase the range, the directionality, and the capacity. So everything that the LTE and the YMax community are talking about is already deployed in Wi-Fi. All the pioneering work is done in Wi-Fi, and it's something that the cellular community is perhaps embarrassed to admit. They don't talk about it, but you want to understand how it works. You look at the underlying stuff, and the Wi-Fi community's already done it. There's a lot more competition in the Wi-Fi space, many, many more vendors trying many, many more different things, because there's a relative freedom from regulatory issues that affect the rest of the community. The good news is the ITU, that is the International Telecommunications Union, has recognized that mobile communications is more than just 3GPP and 3GSM and cellular. They have now officially endorsed that the view of the future includes wireless wide area networks with specs from 3GPP, wireless metropolitan area networks, meaning YMax. They have a subtle distinction there so they can appease all the political forces, and wireless local area networks, 802.11 or Wi-Fi. So the formal top-level bodies have recognized that there's something going on there, and where 3G was the IMT 2000 initiative, what we call 4G is the IMT advanced thing. Now, we've jumped the gun. The ITU's view of 4G was 100 megabits mobile and a gigabit nomadic or semi-stationary. Marketing people have stolen the 4G buzzword and applied it to stuff that's a lot less than 100 megabits, but that happens. That's the way marketing works. So, I won't dive into the deep stuff of technology here, but basically sophisticated modulation, multiple. I have some stuff on MIMO to explain what it is. Simultaneously optimizing everything that people can think of to optimize. That's the quick way to think about what's going on here. Orthogonal frequency division, multiple access. It's basically it is back to the old frequency division multiple access that was used in 1G, except this time there's a cute set of computational tricks that has eliminated all guard bands. If you're an engineer and signal processing guru, there's a thing talked about orthogonal signal structures which don't interfere with each other. In essence, this is a method to allow the different frequency division channels to overlap without interfering. So you can decipher this stuff. It involves doing fast Fourier transforms, which are easy to do with Moore's law in silicon today, so that everything becomes feasible, which would have been inconceivable 20 years ago. The net result is that you can space a whole lot of little channels very close together and use them to send a number. You send, in a particular time period, and you can change what you're doing every 10 milliseconds or every 1 millisecond, which means as you move the handset and the reflection pattern off the wall changes and everything changes about my position with respect to some cell tower, millisecond by millisecond, I can be changing how many bits I'm sending at which frequency based on what happened a millisecond ago. So it's an incredibly efficient way of using the available spectrum. When you put together a whole lot of individuals and combine them into a block of bit carrying capacity spread across all these little subcarriers, it's called statistically multiplexing multiple people onto a block of subcarriers that are being treated as a group. That's orthogonal frequency division multiple access in sort of 50,000 foot level. Another picture, this is from my buddy Fanny Milinarski. Nice graphics, nice color. Again, the issue back in 1G was we had large guard bands between the frequency division things. The issue here is we are statistically sharing a whole lot of things which overlap, but they overlap in a fashion where sophisticated signal processing can pull out the overlapping pieces without interference. The other thing that comes with 4G is MIMO, multiple input, multiple output. The idea here is we can put 2, 3, or 4 antennas on the left, 2, 3, or 4 antennas on the right, and then at any given instant we can send different versions of the signal across multiple paths, and two things go on. First off, we can just get more information across, and the second thing is that if, as I move, certain frequencies fade in because of reflections and funny effects, as something instantaneously fades, I've got another copy that's not faded. And right off the bat, this tends to give 15 or 20 dB fade margin. So it's an enormous increase in capacity, even with a relatively simple use of this approach. And once you have the necessary, and again, the silicon is still evolving. Silicon in the Wi-Fi market today, what's shipping is basically 2x3 MIMO. That is, they can support 3 antennas, but because the antennas are so close together, they're not really independent. So they can support 2 independent signaling across 3 antennas with a little bit of directionality in there. But that computation is increasing at each cycle of Moore's Law. Look out 18 months and we'll be at 4x4 MIMO in the silicon, and then 24 months it'll be in the stuff that we buy and use. So this is being driven really fast, and it's being driven right now by the Wi-Fi community, not by LTE, which doesn't exist, or YMax, which has 10 million deployments worldwide, basically trivial compared to hundreds of millions per chip vendor for the Wi-Fi market. When you go outdoors, what does it look like? Well, there's a guy sitting down in the grass there, and he's actually getting 2 different signals from that tower because of reflections off of buildings and so forth. Once you're doing things like this, there's all sorts of other things you can think of with smart antennas. By directing the signal to different antenna elements at slightly different time periods, you can effectively form a beam, a highly directional signal electronically. This is very marginal right now, but it's in the specs, and as the silicon improves, this will become very dramatic within the next 5 years. Once you get directional beams, you can vastly increase the capacity, because now you reduce interference by picking out people and directing my conversation with you is there and my conversation with you is there, and they're completely independent even though we're in the same room or we're in the same city, what have you. So very, very efficient. There is a minor variation in the spec for LTE and being discussed for the YMax uplink. This is another set of alphabet soup. The short summary is that it's a slightly different coding scheme, and the goal is to improve the peak to average power ratio. In order for the handset, you want to maximize battery life, and therefore you'd like the average signal that you send to be the same. You don't want to have to go and send big power and low power and change it all the time, because in order to be able to handle the big power, your amplifier is going to be dissipating more waste energy along the way. So for efficiency basis, they've got a slightly different kind of optimization, which happens to be called single carrier frequency division multiple access, more alphabet soup. The goal there is to improve battery life. YMax and LTE, they have an awful lot in common. I won't go into the details there. Here's a comparison of data rates and latency at different periods in terms of stuff that's either here now or here in the near future. Remarkably similar. Each side will tell you that they're better, but frankly, the technology is baloney. It's commercial issues and legal regulatory issues that dominate, not the technology. There is one difference here, that the carriers very definitely have influenced the LTE, what's going on, whereas the carriers have had less influence in the IEEE 802.16 process. The other thing is LTE is absolutely, in some ways it suffers from being a break with the earlier cellular technology, and we'll discuss that in a few moments. But much, much more so than WiMAX. LTE is part of the GSM family of thinking, whereas WiMAX is a greenfield thing that doesn't have all the rest of the infrastructure that comes the infrastructure, which is both a burden and an asset. So, commercial issues, LTE, the reality, and I have a thing I'll show you at some point a little later that shows that it's a pipe dream that it's going to be deployed in a commercial sense in 2010. It will take longer than projected. Every other standard has, and there's a lot of reasons why this one will have to. But it is the eventual migration path for all of the GSM community, so it is going to win in the end. Certainly by 2020, it will be the lowest cost and the dominant technology in the cellular service providing space. On the other hand, YMax is not going to go away because there have been frequency-specific blocks of spectrum sold in countries all around the world. So it's reasonable to think that YMax will be a 10 or 15% player, and it will be around in 2020 also. And there are still chances that other things could happen, but it's not going to win in the service provider cellular telephony market that we understand today. This is another way of timing when will LTE actually be available. Look at this interesting table. Down the left are the 3GPP specification releases. They used to number them by year. When they lost track of years, they went to 4, 5, 6, 7, 8. Those are the dates when those specifications were frozen. And if you look from there to when I say first deployed, that's actually what I mean is commercial deployment by 2 or more operators and a number of actual devices that work with it physically available. It takes 2.5 to 4 years from when the specs are frozen until they actually get commercially deployed. So if you bear in mind that the Release 8 freeze, which happened towards the end of 2008, was actually a hurry-up rush job. They froze the stuff that was needed for the chip vendors to get started, while admittedly not completing the rest of it until March of 2009. The best suggestion is LTE will be commercially viable in 2012. Now, maybe it's 2011, maybe it's 2013, but it's not 2010. That's going to be trials next year. And anybody who says otherwise is kidding themselves. So I'm going to skim very rapidly through some stuff about the core network architectures. There are 2 systems widely deployed, one that grows out of the European view of SS7 and intelligent networking, and the other grows out of the American view of SS7 and intelligent networking. The European view is the one that is driving things going forward. But the convergence is a many struggled process, and as you'll see later, there's a pile of other people being added into the soup. I'll just flick through this. It's all in the deck. If you want the deck, leave a card for me and write the word slides on the back of it. I will email it to you. Separately, Carl Ford has said that he is going to send an email to every conference participant on September 8th, that's what he said, with the URL of where the slides will be available on the web. So you can get them by email from me by leaving me a card with the word slides written on the back, or you can get them from Carl on September 8th, supposedly. Signaling in the core network. I got a cute little build slide of all the different things if you wanted the full tutorial. Here's the GSM 2G architecture. The radios and the handsets are off on the left. Circuit switching core network. When they went to add data, bingo. Just added on a bunch of packet stuff without touching any of the original things. You want to move to 3G? Bingo, you just add on the 3G radios without touching anything else. This is building on what you have. That's the way the real world works. You want to go to the next generation? Well, you take the core network and you replace the mobile switch with a soft switch and media gateway. That's what's happening here. So that's Release 4. And you want to go and add, there are 2 things that happen in Release 5. The first on the left is we convert the entire radio backhaul network to ATM. Boy, that was forward-looking. Now, in the next release after that, they converted it to IP. But here's on the left there, we converted the backhaul to a uniform thing, regardless of whether it's a 2G radio or a 3G radio. We have this uniform scheme for backhaul over ATM. And 1 release later, we came up with one for doing it over IP. The other thing that happens here is down in the lower right, we add in IP multimedia subsystem. And that is a plan for how we can do SIP-based multimedia control of VoIP like traffic. And that system was defined a long time ago. It's been touted for a long time. It has been deployed for limited purposes, for push-to-talk, for video sharing, for various new services. It's been deployed for voice in a few greenfield applications, but basically it's had no traction, even though it's been out there for like 8 years. And yet, we'll come to that in a moment, it's critical for LTE. So there's some issues that are going to blow up. 3GPP was the American version, driven with the TDMA and then with Qualcomm CDMA. The goal here at this point is to merge with the 3GPP thing. And interestingly, everybody else in the world who had a different view of SIP and next generation networks, that includes the European Telecommunications Standards Group, ETSI, with their tie-span standards for fixed-line VoIP, the ITU's Next Generation Network Group, the Packet Cable Group that defined the way VoIP works on cable telephone systems. Everybody has pretty much agreed that they're going to come on one Next Generation network. That's 3GPP Release 7, which is defined and is beginning to maybe be parts of it deployed. So there is the hope that all these things will be roughly comparable over the next 5 years. But it is, here's the tie-span version of stuff. A lot of it is identical. A lot of it has other acronyms, so you still have to learn a lot more. You have to learn 30% more acronyms than the base set in order to understand the superset that includes everybody else. The vision here is one core network that will work for all kinds of wireless and fixed access networks, and that it's the other key thing here, the second bullet, access and bandwidth are going to be commodities. Everybody recognizes that now. So the operators want to be in the services business. This, despite the fact that they have completely failed to deliver any of the 3G services they envisioned. And the way they intend to do that is to provide per session quality of service guarantees, which, oh, by the way, would give them the ability to do per session billing, which means that they would be able to bill differently for SMS or voice or internet access. That's the principle. That's what Next Generation Network stands for, and that's where the telephone industry is trying to go. Will they get there? My suspicion is no, but this is absolutely the driving path right now. I won't go through IMS. It's the hype city. Again, the goal is to generate new revenue from new services because they know they're going to become dumb pipes, and they hope to do that by giving you controlled QoS in exchange for differential billing. LTE and IMS. LTE is the first all IP network. It doesn't have any of the legacy circuit switch stuff that was in 2G and 3G. So the only way you can do voice telephony on LTE is to do something IP-based. The official word is that that's going to be IMS, but the practical reality is IMS is not widely deployed, not well liked, it's very complex, and there's a lot of, it doesn't easily connect to a lot of the existing systems. I've heard people argue otherwise, but the reality is it's not being widely deployed. So down at the bottom is one of the quick fixes. The first fix that will be deployed is initial LTE handsets they'll do data over LTE, but they will pass back to 3G stuff to do voice or SMS. The second thing is something called Volga, voice over LTE via generic access. That's an adapter kludge that adapts the voice on the LTE back to the core structures that were your traditional voice network. And the final thing may be IMS. When that happens is anyone's guess. So IMS, the idea, if you compare it, what does it compare to? It most easily compares to the intelligent network vision that was presented in the late 1980s and early 1990s. It was going to free operators from equipment lock-in. It was going to open the protocols so you could get third-party application development. If you look at what happened with the intelligent network, 15 years later, it was a success in some sense. There are about 6 very widely deployed applications which depend upon the intelligent network. 800 phone service, the whole mobility prepaid, voicemail. These are non-trivial applications. They're very widely deployed, and they wouldn't have been possible without the intelligent network. But notice there are only about 5 or 6 of them. They didn't get the hundreds or thousands of applications that the Internet provides. They got 6 applications after 15 years, and there's a lot of reason to believe that that's what's going to happen with IMS. Here is what the 4G core network looks like according to 3GPP. This is called, and I guess if you look at this and compare it to those earlier diagrams, which I won't go back to, this strictly all IP. The block over at the right, which is optional IP services, IMS, is in there. So if you want to do voice telephony, it's a glue-on on the side. This is a VoIP, this is an IP world, and that's why you won't have voice over LTE in 2012. Maybe you'll have it in 2014. Because voice is not core to this thing, it's IP, and yet the operator's voice legacy and existing services and all the provisioning and billing and everything else is based on stuff they've been evolving for 35 years. They're not going to flip overnight, so take a while. Basically, I addressed this at some length in my talk yesterday on broadband, mobile broadband and the services we can expect. The reality is the operators make their money from voice, secondarily from SMS, and everything else is very small. And yet, they all recognize that they're going to become dumb pipes, and the question is, how do we put that off as long as possible? How do we pay for the capital to buy these new radios and new everything that we have to do to remain competitive? That's very much an open quandary. If you want my views on the matter, that was yesterday, and you can get my slides from that also if you want. Put yesterday's slides on the back of your card. I'll mail those too. Voice is where the revenues come from, and yet what's clearly happening is affordable, open, mobile Internet access. If you look at countries where there's real competition, and the UK is doing better than us because they have 5 competing 3G operators, what you find is things are breaking down. Hutchison 3 has just launched. Now, admittedly, it's crippled, but they're now promoting Skype. Now, it's not the regular Skype client; it's a special Skype client which allows you to do Skype to other Skype names, but you can't do Skype to Skype out to PSTN numbers. For that, you have to use your mobile phone, because again, voice revenues are critical to maintaining their. So it's a struggle. But it's pretty clear what people want. They want Internet access. That's all people buy their 3G for is Internet access. That's what the iPhone gave us. It's what Android application stores. The operators are rapidly losing control of the thing that generates the new fancy services. So just like the 3G revolution, the 4G revolution is bringing third-party stuff, not core operator applications. So there's a problem there, and I suggested some solutions yesterday. I won't go into that right now. But it is pretty clear that the Internet is the killer platform. It's not IMS.